Bonjour, and welcome back to QX01, so Introduction to Quantum Information and its Associated Technologies. So let's have a look at where we are at the moment. So far we've covered all these topics, and the latest one was on the notion of operators and measurements. And that is going to lead naturally to a very important concept, the concept of quantum gates, which we're going to do today. We'll see if we can finish or not. And then there will be no lectures for 2 weeks for various reasons. And then we'll resume back in the 19th of April. So far it's on this topic, on quantum cryptography, given by the company KETS. That might change, I don't know yet, it's not fully confirmed, we'll see. If not, in any case, there will be lectures, probably the quantum gates second part will be put in this place. And then so on. So again, no lecture on the 3rd of May, and then there will be a part on quantum algorithm, quantum sensors given by the company Thales, and quantum error correction after that. And then there will be the company Atos, which is going to talk about its quantum learning machine specifically. And then the last lectures will be given by a colleague from Spain on the various technologies for quantum applications, mostly on using superconducting qubits and ion traps. Right. So for today, and probably the next, so this should be lecture 6, by the way. These are the topics we're going to cover. So first of all, we'll start with 1 qubit gates. So we've already seen them, or some of them, so we'll go into a bit more detail of that. And then we'll talk about 2 qubit gates, and in particular the so-called control NOT gate, which is very important. We'll see that there are more than 2 qubit gates, 3 qubit gates. We'll have a look at that. And then once we've done, so we've seen qubit, we've seen gates, then we will be ready to look at quantum circuits, what they look like. And in particular, we will do 2 practical cases as an illustration of quantum circuits. So we will talk about how to create a Bell state, an entangled state that we've seen before. And we will see a small algorithm in a way, or a small protocol, which is the so-called quantum teleportation protocol. And we'll see how we do that. We can do that physically, how we can represent it sort of mathematically, and how we translate it into a circuit. And then at some point, we'll go into a bit of physics. I'll just have a quick word on to one way of creating entanglement using photons. So I will discuss that using nonlinear optics. So it will be very, very short, just to give you some ideas. I mean, the point is not to make a lecture on nonlinear optics, obviously. And in particular, with this, I will bring a typical optical setup that we can use for creating entangled state with photons. Right. So, quantum gates. So the first type of quantum gates that one can make are 1 qubit quantum gates. And we've seen some of them already. They are the Pauli matrices. So first we started to call them sigma 1, sigma 2, and sigma 3. But now we've seen since that we can call them X, Y, and Z, because it makes sense in terms of representation of onto the Bloch sphere in terms of rotation along the Z-axis, along the X-axis, or along the Y-axis. And so basically, in terms of gates, we like to use the notation X, Y, and Z for these various notations. And we represent these gates like this, and we'll see how we put them into our circuit. And is, of course, to have a complete set of gates, we need the identity gate, which is do nothing, which we can represent by the identity operator, but which usually we represent as a line. And just a side note, that with this group of Pauli matrices and identity matrix, and all the permutations that we can think of these Pauli matrices, this represents a particular group, which we call the Clifford group, and we will see later on why this particular group is important. So another gate that we have not really seen so far, so not to be confused with the Hamiltonian, is the Hadamard gate, which we call H. So again, this is not to be confused with the Hamiltonian, which we said is representing the energy of the system. So here it's a gate, it's a particular gate, so you can see the matrix here. So clearly, this matrix is a Hermitian matrix. So we represent that gate like this. And we say that this gate, we call it sometimes the superpositioning gate. And the reason being that, as we will see, is that with this gate, we can go from a particular qubit to a superposition of a qubit. So let's have a look at this. So the Hadamard gate, H, Hadamard gate, H, it's the superpositioning gate. So I'll put it in bracket because it's probably not very English, but what it means is that it's a gate that will be able to create superposition. Okay, so gate to create superposition, and I'll give an example just now. And we will see in a practical case how we use that. So let's say I have my qubit Q0, and let's say that it's not in a superposition state, so it's one of the states, the zero state. And so I can represent it as a column vector, like so. And if I were to have Q1 of 1, sorry, then I would have 0, 1. And now I can apply H, which is given by 1 square root of 2, 1, 1, 1 minus 1. I can apply to Q0 and Q1. So if I do that, so let's apply. So what does that mean, apply? It means that I have the operator H that is going to operate onto the column vector Q0 in this case. So if we go back into mathematical interpretation, it's fine. This is a vector column. This is a 2 by 2 matrix. So we're going to obtain a vector column, which we can call it psi. And what is this going to be? So 1 square root of 1, 1, 1 minus 1, apply to 1, 0. That's going to be 1 square root of 2. And then I will have 1 and 1. Okay? And if I write that back into sort of a basis vector 0 and 1, what I have is 1 square root of 2, 0, plus 1, which is 1 square root of 2, 1, 0, plus 0, 1. Okay. So that is my psi, and we'll see. So now we went from a particular state, so up state, we know it was just up state, to a superposition up in terms of spin, but the zero state, to a superposition 0 plus 1. Okay? So in a way, so we went from a known state to a superposition state. So that's what the Hadamard gate does. So we can do the same on Q1. So we will have psi prime. So that would be 1 square root of 2, 1, 1, 1, minus 1, applied to 0, 1 this time, because I applied to the state vector 1. And that is going to be 1 square root of 2, 1, and then minus 1. So in this case, I would have 1 square root of 2, 0, minus 1. Okay, which is also a superposition state of 0 and 1, but with the dephasing, with the minus dephasing. So if I want to, so this is mathematically, if I want to write it in circuits, and today we said we're going to look into quantum circuits, then I can represent this or this. So in this case, we've seen the order is very important. So we have the ket, the column vector here, and then we apply the matrix to it. But in quantum circuits, we still go from left to right, so it would be different. So how we're going to represent that is by saying I start from Q0, so this is my initial qubit. I do the circuit, so here would be the do nothing, okay, I don't touch it, so that would be the identity in a way. And then I apply the gate, the Hadamard gate, H, and I end up with an output state psi. And that output state is this one. Okay? And if I want to do it for this one, then likewise, I have Q1. So along the circuit, so I go from left to right, and I end up with psi prime given by this state now. Okay? And so I go, this is initial, and then this is final. So I go from left to right. So you will see when you will use the IBM computer, quantum computer, and also the Atos, the quantum learning machine as a test, you will see that you always go from left to right with your initial qubits, your operations, and we'll see many more, and then the final state at the end. Okay. And here, I just want to point out that here there is no measurement done. We've seen the measurement. Here I'm still in a quantum state, so I'm still in a superposition state. I haven't done a measurement yet, and yet I can write that I'm in a superposition state. And well, that's what I wrote here. There is no, at this stage, there is no collapse of the system like we had before, because I have not done a measurement. Okay, I could do then a measurement, which would be represented by this. And that, then we said, either we put 2 bars or a thick one, and that would be the measurement, and no more bracket notation to say that this is a measurement. Well, sorry. This is a measurement. The result is M, which the only thing we can say if I apply it to psi is that it's a 50-50 probability of obtaining 0 or 1, because I don't know in advance what I'm going to find. Right, so that's our first circuit, very easy, small circuit. One quick note is the Hadamard gate. You can see H dagger is equal to H dagger H in its identity. So it's what we call also unitary matrix, so it's reversible. I can go back and apply reversibly and end up go from the end to the start. And that's the notion of reversibility is very important. So there are more 1-qubit gates. So there is, for instance, what we call the square root of x. And we've seen the x gate is the equivalent of a NOT gate. If we go back here, the x gate is a NOT because what you do is you take 0, 1 and you transform into 1, 0, so it's reversing it. That's a NOT gate. But you can realize sometimes a square root of NOT gate. And what it means is that, so it would look like this, and the symbol is something like this. Sometimes you find other symbols. Sometimes you just, in the square root of NOT. And so how do you get that? And what we call square root of NOT is, because, well, if you apply it twice, so if you do square root of NOT, square root of NOT, so if you apply this matrix twice, then you end up with the X matrix. So in a way, the square root of NOT squared gives you back the X. That's why by language we call this the square root of NOT. So let's have a look. So that's the second one. That is also interesting. So one question you may ask is that, you know, why do we have so many gates? Why do we have different gates? And the main reason, as we'll come back to that later on, is because it depends on the system you use. So again, physically, you have physical systems. It could be superconducting circuits. It could be photons. It could be ions trapped in a trap. And depending on your system, there are gates you can do easily, and gates you cannot do easily, and some that you just cannot do. Okay, but as we will see, you can by using these different gates, what is important is you have your complete set of gates in order to have potentially all universality of a quantum computer. And as long as you have this, whether you use a square root of x, or as we will see, a so-called phase shift gate, and so on, then as long as the right combination is applied and your system can make them, then you're fine if it's enough to be able to build any universal quantum computer. Okay? We'll come back to that later. So let's have a look at that. So I just want to show you that, so square root of naught, so the square root of x, so the definition is 1/2, and then 1 plus I, 1 minus I, 1 minus I, 1 plus I. And so if I apply it twice, so I multiply them together, I've got 1/2, so 1 plus I, 1 minus I, 1 minus I, 1 plus I, times the same thing. So I'm going to have 1/2, and then, so this times this, that's 1 plus I squared plus 1 minus I squared. And then I have this times this. In this case, I've got 1 plus I, 1 minus I, and 1 minus I, and 1 plus I. So that makes 2, 1 plus I, 1 minus I. And then this term is going to be the same as this one. So 1 plus I, 1 minus I. And then this time times this time, which is 1 minus I squared plus 1 plus I squared. Right? So now, if I look into this, so I can develop, or, you know, there are various ways you can do this. The good thing is I only need to know two terms, this one, yes, twice. So if I look at this one, so I have 1 plus I, so that's 1 minus 1 plus plus 2i, and then the other one, which is plus 1, minus 1, minus 2i, because it's twice this. So everything goes away. And then for the second term, it's going to be 2, 1, plus 1, because it's I minus I, it's I squared minus I squared, rather, so it's plus 1. Here it'll be the same. So that's going to be, did I get it wrong? Let's see, maybe I got it wrong. Let me see. I've got a squared minus b squared, so a squared, wait, that's it, no, this is it. So we have 1 plus 1. So here it'll be the same, so 2, 1 plus 1. And then here it'll be the same as here, which is 0. Okay. So what I end up with is 1/2 of 0, 0, and then I'm going to have to have 4, 4. That's going to be 2, 0, 1, 1, 0. So if we forget the factor, the factor in front, we regroup the x gate here. Oh yeah, I know I got it wrong, because I've got 1/2 here, so I've got 1/4 here. 1/4, 1/4, and then no more. There we go. It's much better. Okay, so so that's why reversibly, that means this gate can be seen as the square root of x, because when we apply it twice, we get back x. So and then there are other gates, like I said. So here's a more general gate. We call it the phase shift gate, R psi. And so it's a general gate which, when phi equals pi, is basically the z gate. And the z gate is 1, 0, 0, minus 1. And if it's pi over 2, we have what we call the S gate, which is actually a square root of z gate. So again, what it means, the square root, is that if we apply it twice, we obtain z. And then if we have pi over 4, we have what we call the T gate, which is square root of S, which is the fourth square of z. So that means if we apply the T gate 4 times, so T to the power of 4, we end up with the Z gate. Okay? And so in particular, so we will see that these gates are very popular into the superconducting qubits that we call sometimes transmons, or that the people who make those call transmons. And you have here a typical superconducting circuit where you see there is a gate capacitor in a circuit here with a Josephson junction that gives you the nonlinearity necessary to create a qubit in here. But this is just a preview. We'll see. We will see that much later on how it works, not in full details, but to give an idea. What the message to take here is that with these gates in particular, transmons are very good to create these gates and not so good at creating others. Okay. So that was for 1 qubit gate, but then we have 2 qubit gates, and in particular, what I call the inevitable control NOT gate, or C-NOT gate, which is also sometimes called the control Pauli X, as we will see why, because it's basically the combination of identity and a Pauli matrix here, the X Pauli matrix. So here's the C-NOT gate. So it's a 2 qubit gate, so you need to have the 4 components. And so let's try to see what it does. So it's a very important gate. It's an extremely important gate, and we'll see why. But unfortunately, it's also a gate that is not so easy to obtain experimentally. Because you need a 2-qubit interaction for that, which physically is not easy thing to do. Okay. So let's have a look at how it works. So sometimes what we say is so the control node, the C node, the control node, there is already the name given into is that it's a gate that is going to control. So it's a qubit that is going to control the result of another qubit. So sometimes what people use, they say that in a control NOT gate, you have 2 qubits, so Q1 and Q0, is that one is the target and one is the control. Okay, so if I want to, so you have your first qubit, Q0. I have to see which one's which. So let's take the diagram as it is. So Q0, and then Q1, and then I have the representation of a control NOT gate is like this. So you can see already. So now you have two qubits each line, and then you have this segment because you're going to make an operation that will depend on another qubit, on this one, depending on this one. And so what you do is that we call it, so this one is a control, and this one is the target. And what you say is that you say if the control, so if control is 0, then do nothing. Okay, so that means that so target remains 0 or 1 or any others or superposition. Okay, so what it says means that if the control is 0, whatever comes in here, you just leave it alone. So if it's 0, if Q1 is 0, then it's going to be 0. If Q1 is 1, then it's going to be 1. On the other hand, if the control, so if control qubit is 1, then inverse. Okay, flip. So that means that target will change from 0 to 1 or from 1 to 0. Okay? Let's get rid of that. Okay, so the target is modified. You just flipped it. So if I want to treat that in a 4x4 matrix, that's what it looks like. We can see, so this part here is the if 0, do nothing. So the do nothing is just the identity matrix for this part. But if 1, then inverse, and inverse is a NOT gate, so it's X gate, so inverse is NOT, so X, and the do nothing is identity. So identity is 1, 0, 0, 1, and inverse is 0, 1, 1, 0. And we see that the combination, so of the two in a 4x4 matrix, because we have 2 qubits, so we need potentially 2 entries of each, so that's a 4-column vector. then the matrix is going to be this one, so 1, 0, 0, 1, and then this part is 0, 1, 0, 1. Okay? So, so I can have a look at what it does on a particular state. So so for 2 qubits, so Q0 and Q1. So I start with 2 qubits. So separate 1 plus 1. Now I want 2 qubits. If you remember, the operation to do this is to do the tensor product. So I do the tensor. So say Q01 was A0 plus B1, and Q1 is C0 plus D1. Now we've seen that if I do the tensor product of these two, I'm going to obtain a 4-column vector. So I'm going to obtain Q0 tensor product Q1. That we've seen I can rewrite it like this, Q0 Q1. And that is going to give me the A. So I can, let's write it rather like this. Alpha, beta, gamma, delta. And we've seen that I can rewrite this as being A00 plus B01 plus C10 plus D11. Okay? In terms of 2 by 2, or if it's a 4-column vector, then it's A, B, C, D. So I'm going to have A, B, C, D. Okay? So that's the most general state, 2-qubit state I can send in. Okay? And now, so this is my entry. So now it's tensor product between these two. That's why those are linked now by the tensor product operation. So I've put them together that way in the same mathematical space. And now I can apply the C0 gate onto this state. So this, let's call it psi. So let's have a look. So C0, so C0 onto psi is going to be this matrix. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0, applied to A, B, C, and D from this 4-column vector. So here you go. What I obtain is a 4-column vector, and that's going to be A, and then B, and then D, and then C. And what I can see is that indeed the first 2 components we do nothing. Okay, and the second 2 we did a NOT or reverse C and D. Okay. So this one is the control, and this one is the target. That's control, and that's the target. Okay. And so we end up with a psi state at the end, sorry, psi prime now because we control not it, that is going to be again a 4-column vector. Okay. So, yeah. So we can generalize a C0 gate by this gate, which is also a 2-qubit gate, where we generalize this part by saying that this part is, so we call it the control U gate. And so the control NOT, we can write it CX for the reason we said, because X is the NOT gate, so we can call it control X. But the more general matrix would be a unitary matrix, so a Hermitian matrix with the right properties, as we said before, U, with 4 coefficients, so those coefficients would be complex coefficients, and with the right properties of normalization, and they are linked together because it's a Hermitian matrix, unitary matrix. And so the control U gate is going to look like this, where it's the same as here, but you generalize this part, where now what you say is that if the control is 0, do nothing, that remains, that part. But if the control is 1, then you don't just do an inverse, but you apply this matrix here, so this U matrix, with coefficients that you can decide to put in, as long as you verify you have a unitary matrix. And so, in fact, the C0 gate is a particular case for where you have 0, 1, 1, 0. Okay? And so like this, you could have all the 3 Pauli matrices here, so X, Y, and Z. So those would be particular cases, so Cx, Cy, Cz. And so what I want to say here is that all you need is using this Clifford group I talked about, and Hadamard gate, which is a single qubit gate, and or T and S, and a 2 qubit gates with the C0, then one can show that this is enough to build a universal quantum computer. Okay, so you don't need more than that. So basically, in other words, if you can make a C0 between 2 qubits with this property, if you can manipulate single qubits through quantum gates, like the ones that we've just seen, Pauli matrices and Hadamard, then the set of those is sufficient to build a quantum computer. Okay? The reason being that, of course, here you have 2, but if I want to bring another one, then I can bring another qubit, and so far this qubit does not belong to the others, but I can, of course, incorporate that new qubit in a way. We'll see an example with quantum teleportation by doing a C0 gate between this one and this one. So now this one is linked to this one, and this one is linked to this one. So by property, group property, this one is also linked to this one. And I can go and so on and so forth. I can manipulate single ones, and all I need to do is to entangle. So the control NOT gate is also some form of entangling gate, where I can now link another qubit Q2 and then 3, 4, 5, etc. to any of those by applying a control NOT gate. So by next neighbor 2 qubit gates, I can entangle, and I can have a 8, 16 or million qubit column vector and computer. So, oops, sorry. Okay. Okay, so we've seen 2 qubit gates, and the particular one is the C0 gate. But likewise, the 1 qubit gate, we can have other 2 qubit gates, depending on the system. So in particular, the swap gate. So you can see here how we have the sign for the swap gate. So it could be either that or just this sign. And what we do basically is we start from Q0, Q1, 2 qubits, and then we exchange the 2 qubits, okay, and by the swapping mechanism, and that is what the matrix is going to look like. Okay, so you really swap the two components. So we can have a look at what it does. So let's have a look at this. Okay, so we're going to start with the same idea. Okay, let's remove everything. Well, we start from a 4-vector column with coefficients A, B, C, D. And we have 2 entries. Okay, so Q1. And then we have the swap gate. And what it does is it gives me Q1 and Q0. So let's have a look. So let's start from psi, which is going to be Q0, Q1. So A, B, C, D, like earlier on. And then I do swap gate to psi. So I apply the 4x4 matrix. So it's 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, then 0, 0, 0, 1. So if I apply this to A, B, C, D, the vector column A, B, C, D, I'm going to obtain a 4-column vector, which is going to be A, and then C, and then B, and then D. So we can see in this case that we swapped B and C here. And that's, so if I translate that, what I have is A0, 0 plus C0, 1 plus B 1, 0 plus D 1, 1. Okay. And so what I did effectively, again, so I swapped these 2 coefficients into the middle. And basically, that's equivalent to reversing the Q1 and swapping the Q1 and Q0. So that's another one. So like I said, we can have the square root of that. So again, the idea is, so usually it's written like this. You have a half in the middle here. And why is it square root? Because likewise earlier, with the single qubit one, if you apply this gate twice, you're going to end up with the swap gate. And there can be other ones, also more perhaps specific ones, again, depending on the physical systems. But at the end, what matters is that if you can show that if you have a universal set of single qubit operation and 2-qubit operation, then as these 2 qubit gates or operations in a way are a way of mixing, entangling the qubits together, then that's enough to go from 1 qubit to the next, Also, you can also imagine, it doesn't have to be physically next to it. You can also decide to swap this one and this one afterwards, for instance, and then so on and so forth. But you can also see how the complexity of this can occur very quickly. Because down here you have to apply this matrix to Q1 and Q2, and then have something else, so Q3, and then here is going to be something else, and so on. So the nice thing about the circuit representation, of course, is that all of this can be represented by simple lines and various connections. And so if you will do that for your sort of practical work. If you use, so in typically for instance, the IBM machine, it lets you move and place different qubits, initialize them, place your different gates, and see at the end results, measurements done, and see the result. Okay, and all at the back, what the machine does is that it makes all these matrix and vectors calculated. You don't have to do. Right. There are also more than 2-qubit gates. So those are more exotic in a way, but also interesting on their own. We're not going to see them too much, but as they show up for various reasons, I'll give them to you. And the two sort of most famous ones is the Tofoli gate and the Fredkin gate. So both of them are 3-qubit gates. So if there are 3-qubit gates, that means you need to have 8 by 8 matrix, because you need now 3 qubits, and we said 3 qubits is an 8 vector column. And you can see the Tofoli gate, it's sometimes we call it a control-not gate, okay? Because what it does is that you have a control and a second control, and then you have the target. So, and you can see here that the Tofoli gate is mostly, you can see this part, is mostly the identity matrix. Okay, so the first two is do nothing, except if both of the control are in a particular state, then you swap the third qubit. Then you do a control X, you do a X gate here. Okay, so if all the states are the same, for all the states that are not the same for the first qubit and the second qubit, do nothing, and you do something only in one particular case. Okay, when both of them are 1-1, say, and then you do something to your target. Otherwise, most of the time you don't do anything. So that's that, and then you have the Fredkin gate, which is the equivalent of the swap gate before 3 qubits. And this one is sometimes called a control swap gate. Okay? So what you do is now you do a swapping depending on the control of a third qubit. Okay? So you would have a control qubit, and then what you do with the Fredkin is the control here is going to give you the swapping. Okay? So that's why here you do nothing in this case, and then in this case, there's one particular case where the control tells you now you have to swap. And so you swap the other two, and you exchange Q1 and Q0. So like I said, so those are specific gates, so they are very interesting, but as you can imagine, physically, if it's already difficult to make a 2-qubit gate, like a control-not gate, you can imagine that this is even more complicated. Although it's very interesting in terms of calculation, because those gates are fully reversible. And that's very nice, but very difficult to implement. So that's why it's not something that is used so much. And it can be used in very specific algorithm. Right, so this is it. So now we're equipped. We've got single qubit gates. We've got 2-qubit gates, even 3, although we won't use them so much. So, okay, now let's see. We've seen already our first circuit, so let's go a bit more into quantum circuitry. So the first question is, on a single qubit level, I can apply various gates. Okay, I can do one and then do another one. So if you remember, there's one thing we need to be careful, is that the order in which we write operators matters. Okay, so if you remember, so we said that, so if I want, so say I have my starting qubit psi, and I want to apply x and y. But what we said is that in some instances, orders matters, because we said operators do not necessarily commute. So if I have two operators A and B, this is not necessarily 0. So in other words, if I apply B first and then A, it's not going to give me the same result that if I apply B first and then A first and then B. Okay? So that's what we said. So we wrote it. We say okay, I want to do a C, I call it C gate. And the C gate is a combination of X and Y. Okay? But it's particular, it's X, Y, but if I write it like this, that means I do Y first, right? And then I do X second. Okay? And the way to see it is because, well, if I apply C to psi, then what I do is I do X and then Y of psi. But what I effectively do is I do this first, and then I do this second. Okay? Well, it's basically matrix calculations on a vector. If I write it like this, if these are two matrices, then that means I apply first this matrix to this vector, obtain another vector, and then I apply the second matrix. So here's the same with gates, except that now, as I said earlier, if we want to write this as a circuit, then as the circuit goes from the initial state on the left-hand side to the final state on the right-hand side, then basically I have to reverse the process and say that the equivalent of that in quantum circuit would be psi, and then first I apply, let's make something straight, first I apply y, because that's what I do first, so if I go from left to right, and then I do x, okay, and I obtain something else, psi prime, okay. So sometimes, so most of the time the representation is like this, where you actually put the gates one after the other. Sometimes you may see this representation, although it's not used so much, which is the XY product, with the dot product, and because this looks more like the matrix notation where you do X, Y, so you do first Y and then X in this case. So this is one of the rules that we need to know. And then we said that if we go from two single qubits to a two qubit state, then effectively, mathematically, what we do is we use the tensor product to enhance, to augment our space. So how do we do this? So for instance, I can take 2 qubit psi and phi. So I can take psi and phi, and I'm going to apply a gate on each of them. So I can do that. Okay, so I can do psi. So I apply the gate y on this one, and then I obtain the result psi prime equals y psi. Okay. I can do the same on phi, another qubit, but this time I apply x, and I end up with phi prime, which is going to be x of psi. Okay? But now if I want to incorporate these two separate operations into a 2 qubit operation, I can do that. We've seen how we do this. I can tensor product it, and for that I need to tensor product the two gates. So we've seen how we do this. So the combination is going to give me C, for instance, and I go from this. Then I would go from this to this, where now I have a common gate, C, which is a combination of X and Y for each of them. Okay? And I will have 2 outputs. Okay, so in this case, I call them phi prime and psi prime, and phi prime. which is tensor product. So this would be psi, phi, psi prime, phi prime. Now, if I look at this C component, this C 2-qubit gate, so C is tensor product of Y and X. So I just use the definition. I take the matrix on one side, I take the second one, operators, gates, it's all the same, and I tensor product. So we've seen how to do this. Y is 0, I minus I 0, tensor product with X, which is 0, 1, 1, 0. So if I develop it, so I'm going to have a 4 by 4 matrix now. So if I develop it properly, I have 0, so I have 4 terms, 4 times 2 terms, so 0 and then 0, 1, 1, 0. I, then 0, 1, 1, 0, minus I, 0, 1, 1, 0, and then 0, 0, 1, 1, 0. Okay? So this gives me 0. So I've got 4 terms, 0, 0, 0, 0. And then here I will have also 4 terms here, 4 terms there. And that's what they're going to look like. So if I carry on here. So let's see. So now C is Y tensor product X, and it's so 0, 0, 0, 0, 0, 0, 0, 0. That's for here. So in fact, I should write 2 missing. And then here I'm going to have 0, minus I, 0. And then here I'm going to have 0, I, 0. Okay. And that is my new matrix C, which is a 2-qubit matrix now applied onto psi and phi. And that's going to give me psi prime, phi prime, a 2-qubit 4-vector column state. Right. So another very important example is if I go back to the Hadamard rotation, single quantum gate, is when you apply Hadamard gates to several qubits. And the reason why you do this is because I told you the Hadamard gate is a very important one because we've seen that it's the one that goes from a particular state, so say 0, 1, to a superposition state of 0 plus minus 1. Okay? So that was true for 1 qubit, but also true for n qubits. So when you tensor product the Hadamard gate between 2 qubits, 3, 4, 5, n qubits, then what you do is a very important gate. So sometimes there are some algorithm that starts like this, where you take all initial state of 0, and then you tensor product Hadamard on all of them. And when you do this, you create a full n-qubit entangled state. Okay, so that's why it's a very important one that is used because that's sometimes is your starting point where you want to have everyone on a superposition state. It's not necessarily something you want to do all the time because that requires a lot of physical implementation because you're going to superpose all the qubits together. But sometimes for some algorithm, this is your starting point. So let's have a look at what it looks like for 2 qubits. So I want to do Hadamard onto 2 qubits. So I tensor product Hadamard on one and Hadamard on the other one. So sometimes we write it like this, H2, so nothing to do with dihydrogen, but simply the fact that you do Hadamard on a 2-qubit tensor product state. So what it looks like, well, let's do the same thing. So you have 1 square root of 2, and then you have 1, 1, 1 minus 1. That was the Hadamard gate. Tensor product with 1 square root of 2, 1, 1, 1 minus 1. Okay, so that's H2. So this is going to be a 4 by 4 matrix. So how is it going to look like? Well, I'm going to apply the same rules as here. Let's have a look. Let's have a look at that. So H2, so the 1 square root of 2 is going to give me 1/2. So I have 4 by 4, so I have 1, 1, 1, 1 minus 1. Okay, and then for each of them I have again the matrix 1, 1, 1 minus 1. So 1, 1, 1 minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1, and then 1, 1, 1 minus 1. And that's going to give me 1/2 of, basically all of those do not change. So 1, 1, 1, 1, then 1 minus 1, 1 minus 1. Here it doesn't change either, so 1, 1, 1 minus 1. And then here I change the sign, so I've got minus 1, minus 1, minus 1, plus 1. Okay? Right? So now if I do this, let's have a look at what it does on a 2-qubit state. So I told you that the Hadamard gate, when it's applied n times, or tensor product n times, it gives all the superposition state of all the qubits. So for 2 qubits, that means that this matrix should be able to give us, we've seen before, what a general 2-qubit state would look like this, where you have 0, 0, 0, 1, 1, 0, and 1, 1. So let's have a look. Let's apply now this to, say, 0, 0. So you send 2-qubit state. So what you do, so the equivalent, so you have got Q0 equals 0, and then Q1 equals also 0, and say this is your initial state, your 0, 0. And then you apply to these two the second order Hadamard gate, and you're going to end up with the result. So what you do is you apply this to 0, 0. 0, 0 is given by, we've seen before, the 4-column vector 1, 0, 0, 0. So H2 on 0, 0 is going to be this matrix, which I'm not going to write again, and then onto 1, 1, 1, 0, 0, 0, 0. And that is 0, 0. So if I do that, so now I can, let's write it here to make it easy. So 1, 0, 0, 0. Then I end up with the 4. I've got, sorry, I forgot the 1/2. So I've got here 1/2. So let's have a look. So I have, this is 1. And then this is also 1. And then this is also 1. And then this is also 1. And so effectively, I do have 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. 1/2, 0, 0, plus 0, 1, plus 1, 0, plus 1, 1. Here we go. Okay. And so if you apply it to an n qubit register, you perform what we call it Hadamard transform, because basically, so you go from the state 0, 0, 0, so you've got n qubit, to a superposition of 0, 0, 0, 0, 1, 0, plus 0, 0, 0, 1, and so on and so forth. But all the combinations of all the possibilities given by a n qubit register, n being 3, 4, 5, 10, 50. And with the rule that the number of terms that are 2 to the power of n. So for 50 qubits, 50, the 2 to the power of 50 is just tremendous. Okay. Hence, again, the power of the quantumness in these technologies. Right. So let's have a look at practical cases. So I have two practical cases I want to look into. First, so as an exercise, the first one is to create a particular Bell state. So I want to create the Bell state that is there, so phi plus. If you remember, we define the Bell states for two states because we can show that they are what we call maximally entangled state. And we name them, so there's phi plus minus and psi plus minus. So I want phi plus, so it's 1 square root of 0, 0 plus 1, 1. So how do I do that? So let's have a look. So we'll do it. So I'm already giving you the quantum circuit. It is going to look like this. And then we will see in details how we translate that quantum circuit into calculations, and indeed see that by applying this quantum circuit with the rules that we've seen, Hadamard, control not, the base state. So you can see already that what I need to have this particular base state, I need to do an Hadamard gate and then a control not gate. And that is going to give me the phi plus state. So let's do that. All right. So I start off with 2 qubits, so Q0, Q1. And what I do is I initialize them to the state 0. This is, by the way, something very important. So later on, I will give you what is called the Divincenzo Criteria. And the Divincenzo criteria are 5 criteria plus, there is the extended plus 2. But in the 5 ones, as we'll come back to it in more details, the first one is to be able to initialize your qubit. I mean, that sounds like not a difficult thing to do, but it could be for some systems. So the first one is to be able to control the state you want to put in. So if you remember, for an electron spin, for instance, the spin can be up or down, so which could be the 0 state or the 1 state. So what I'm that I should be able to control the electron spin of my electron. So for that, it's fairly easy. I can put it in a magnetic field and then orientate the spin into the up state. So I can initialize it into the state that I want. Okay? For photons, polarization state, all I need to do is use a polarizer. Then I fix the polarization state and I initialize it in, say, vertical, which is, say, the 0 state. Okay, but this is very important. Sometimes even the initialization is not so easy. But let's go back to the quantum computing part. So I start with 2 qubits. and both of them initialize into the 0 state. And what I do is I apply on the first qubit a Hadamard gate. Okay, so up to here, these two qubits are still sort of separated. I can tensor product them, but in a way they're not related with each other. And in order to entangle them, that's why I said sometimes the C0 gate is called the entangling gate, because if I apply a C0 between Q0, qubit Q0 and Q1, then I will now entangle the properties of these two and end up with the state that is going to be the phi plus state. So 0, 0 plus 1, 1 over square root of 2. Right, so let's go step by step. So first of all, I initialize my two qubits. That doesn't work, we said. So initialize in 0, 0, and I tensor product them. So this is a mathematical operation where I now say they are not two qubits. I actually have a 4-qubit space. Okay, so that's the first thing to do. Then on Q0, I apply Hadamard gate. So if I apply Hadamard gate, so H on Q0 is going to transform, so H on 0, and we've seen that just before, earlier on, that this is going to give me the superpositioning state, so 1 square root of 0 plus 1. Okay? So now, and I go from left to right. So here, so I started with 0, tensor product 0, and I end up with 0, 0. So here, this is step 1. So step 1 is, say, from here to here. Okay, so step 1. Okay, where I tensor product. Again, I go from left to right. Then step 2 is going to occur here. So step 2, the Hadamard gate on qubit 0. So now at this stage, so now here I was at this stage, and then at this stage, or here or there, it doesn't matter, huh? The wires don't count. I am in that, so this is on qubit 1, but I have, what I actually have is a tensor product of the two, so what I have is now 1, so at this stage, I have, so how am I going to call it, say capital Q, 2 qubits, I have 1 square root of 2, and then I've got 0, 0, this one hasn't changed, and 1, 0. So 0, 0 plus 1, 0. Yes, that's right. Okay? Because again, this is qubit 0, this is qubit 1, and qubit 0 has been. So this is qubit 0, and this is qubit 1. Okay? So in other words, this is what? This is H Q0 tensor product Q1. Therefore, it's 1 square root of 2, 0 plus 1. Tensor product 0. And we said that the tensor product in this case can be seen as a multiplication product. So it's 0, 0, and 1, so 0, 0, and then 1, 0. So this is this. Okay? So this is step 2. Step 2 now is this sort of space, new. So if I want to develop it, so I can do it like this, or I can do it like this, where I can tensor product the operations, where I said that what I do here is I take the tensor product of Adama and identity, because this is identity. So I do the tensor product of these two. So we've seen how to do that. So I do H and tensor product I. So this is what it looks like. I end up with a 4 column vector. So it looks like this. So 1, 1, 1, 1, 1, you see, and then minuses and so on. And if I apply this K, so this new matrix that I call K, which is the tensor product HI, so K is the tensor product H and I being identity, because I don't do anything in the second one. To the state 0, 0, because that's my initial state. This is the 2 coming in. Now with this common matrix, I end up, so I can do it. I'm not going to do it, but we can see it's fairly easy that I'm going to end up from 1, 0, 0 to 1 square root of 1, 0, 1, 0. So 1, 0, 1, 0. So yeah, let's write it like this. 1, 0, 1, 0. Remember with the we said that definition for a 4-qubit state is that when you write it, this is 0, 0, this is 0, 1, this is 1, 0, and this is 1, 1. And if you remember a way of remembering it, because for instance we never know which one we put first, is that you should put it in order that you would count binary. So if you count binary, this is 0, 0, this is 1, 0, this is 2, 0, and this is 1, 1. So in order is 0, 1, 2, 3, if you want to do binary on your hand. So if you were to have 3, and we've seen that before, it's 0, 0, 1, 0, 0, and then 2, 0, 0, and then this one, and then this one, this one, this one, and so on and so forth. And then at the end, you've got these 3. Right. So that means I've got this one, and indeed, this one and this one are the ones that are found by this calculation. So I do have indeed this state. Right, but it's not quite what I want, because what I want is this. Okay. So, and we can see that this looks like a control not operation, because the only difference between this state and this state is that I swapped this guy from 1 to 0. And this is exactly what we do. So this guy says, well, if I'm in that state, don't do anything. But if I'm in that state, then swap. Right? So it's a control not operation. That's why if we now apply, so that's the third step, if we now apply the control not, then I'm going to be in the final state. So how am I going to do this? So I do a control not. So control not with the matrix that we've seen before. So it's here. Okay. And now I apply it to that state. So 1, 0, 1, 0. And you can show, and you can see here, if I multiply this by this, I have 1. This by this gives me 0. This by this gives me 0. But then this by this gives me 1. Okay. And so then the third step is the control not onto that new state, which I have not CS, I did give a name, so it's Q. So onto Q. And that is going to give me the psi plus, which is 1 square root of 2, 1, 0, 0, 1. And that 1, 0, 0, 1 is exactly what I wanted in the first place. Okay? Right. So here is a practical case. So again, you can see the power of quantum circuitry, because by doing this, which is simply, and even that I added some terms, but what it looks like is simply this. So I take 2 qubits, apply H to the first one, control NOT with the second, and then here we go. That's it, done. Okay? As opposed to all of what I've done mathematically, and even then I didn't write everything down in order to find the same result. Okay? So we can see how useful the quantum circuitry notation is. Right, so that was the first practical case. So now let's have a look at the second practical case. So the second practical case is a very interesting one. So let's have a step back. Because the second one is what we call the quantum teleportation protocol. So there is something you need to know, is that physics tells you that Star Trek was right. And in fact, it was quite right. So if you're a fan of Star Trek like I am, you know that one cool thing that they do in Star Trek is that they have this teleporter. So they didn't call it quantum teleporter at the time, but they have this machine that allows to teleport people from their ship, from the USS Enterprise, to a planet to visit. Okay? And if you remember, if you've seen Star Trek, you know that what they do is that they disintegrate the people there and then make them reappear somewhere else. And that somehow, they didn't know at the time that quantum teleportation was possible, that physics tells you that quantum teleportation is possible. That has been shown since. And that they didn't know that, but the instinct was right. Because what does it mean, teleporting? So teleporting means that you need to destroy the original state. So if I talk in terms of qubits, so the original U has to be destroyed in order to reconstruct U somewhere else, right? First of all. So that means, by the way, if one day someone tells you, hey, please come into my quantum teleporter, better make sure that it works first, okay? Because if it's a real one, it's supposed to disintegrate you first before reconstructing you somewhere else, okay? So that's first of all. And the second thing, and that's, of course, disintegrating someone is not so difficult, but the second rule is much more important and much more difficult, at least for people, is that you need to be able to, we should be able to entangle you as you were, so that when we reconstruct you with, say, atoms from the planet that we put, because at the end of the day, that's what we are made of, so atoms, and there is nothing, carbon atom on space, on Earth, or on a planet is still a carbon atom. But what is different from two carbon atoms is the quantum state that they had, okay? And that's why in order to reconstruct you, we need to entangle you in order to make you so that you're in a superposition state, so that at the end, when we measure you, when we see you back on the planet, we collapse your wave function into you. And basically got rid of you that was on the ship. So that means we need something to entangle you with, so that we have this information, this quantum information that we have not measured, this entangled information of you on the planet, and then be able to reconstruct you. So that these are the three things. So first of all, you will be destroyed, because we've also, if you remember, I told you that there is, in quantum physics, and it's also why all of this works, there's a very important theorem, is the no cloning theorem. So physics tells you that I cannot make a perfect copy of you. So teleportation means that we need to destroy you somewhere in order to reconstruct you somewhere else. Okay? We cannot make a copy of you. That's the first thing. The second thing is, in order to do this, and we'll see this protocol, is we need to find a way to entangle you with particles in order to get rid of you on one side and to reconstruct you on the other side, knowing that the information of you is kept through this entanglement between ship and planet. And then, it's not finished, of course, is once we've, when we reconstruct you on the planet, we need to make some adjustments on the entangling part in order to make sure that it is you and that we haven't got rid of you somewhere and teleported, in fact, someone else in a way. Okay? So those are the three ingredients. So I'm going to show you, so this is, sort of a cartoon but true picture of quantum teleportation. The ingredients are here. So we need to destroy the original state, we need to entangle it, and we need to measure it and to adjust the final result in order to make sure that we have what we started with. So those are the steps to do. So how do we do this in practice? So of course, I'm going to show you an article. So of course, quantum teleportation for you and me is, although physics tells you it's possible, as you can imagine, we've seen that now. That means we need to entangle each of your states, of your quantum states, or each of your atoms, in a way, in order to be able to teleport you. So as you can imagine, we are made of billions and billions and billions of atoms. So that doesn't seem very reasonable. Although it's possible, it doesn't seem to be something we will be able to do in the near future, unfortunately. Okay? But we can do teleportation, and in fact it has been done in labs on physical system onto small system, onto single qubits, and in a way that's all it matters, because for quantum computing, as we've seen, we only need to do operations on 1 and 2 qubits. So that's all we need. And we can do that, so I'll show you later on, that this was done experimentally using photons and also spins. Okay. And also some other physical properties, but the fact is we can do it, we've done it. So it works. Okay? Because quantum teleportation is not a fantasy. So how do we do this in practice? So we're going to see, again, in this case, how we go from state characterization, so all of this, to quantum circuits. So first, because it's a bit more complicated protocol than the one before, let's, again, have a step back. So have a closer look of our actual system. So if we talk about qubits, what we want to do here is we want to teleport a particular C and then teleport it somewhere else. But what we're going to do, as I told you, 3 qubits altogether, because we need the original qubit to be teleported. And we need 2 qubits, 2 entangled qubits, one that we're going to entangle with our initial state, and one that is going to be the one that is going to be transformed into the original one. Transform or get the teleportation effect of the first one. So we need A, B, and C. A and B in this scheme are entangled, so we need a source of entangled qubits, so we need something that can provide this kind of Bell state. And to do a particular measurement, so that would be the transmitting station, where what we do is we do a joint belt measurement between C and A, and what it does basically is that you go from C to, and you take C and A, and in a way what you do is you entangle C with A. And as you entangle C with A, as A is entangled with B, you entangle C with B. And that is the one you want to teleport. And by making a joint measurement here, so when you make a measurement, you destroy the original C state, and I told you this is necessary. You need to make a measurement means you're not quantum anymore, you're classical, so you need to destroy C. So that's what's called the Bell measurements. So that's at this transmitting station. And then you're ready to get the information from C to B through this joint AC measurement, except that you need, maybe, we'll see how you may need that, you may need some tweaking. So what I'm saying by that is you have to make some adjustment to the B part, the B qubit, in order for the B to become C. And then basically teleport C from one place to another one. Okay? So quantum teleporting means what? That you need, so first you need a qubit to teleport, so that would be 5C. You need to be able to create a pair of entangled qubits, A and B. So this is it. So as of now, so far, they are separated. Then the third step is you need to make these Bell measurements between A and C. So you need to make a joint measurement. So what it means is you, in a way, you can see it as a collapsing together A and C. You will find a specific result. You will find a result, a measurement. You need to transmit that result. So that's the classical result. You need to transmit that to B so that you can apply the right. So you don't measure B because you don't want to measure it because you want to teleport C from one place to the other. So teleporting means that you remain in the quantum state. Okay, that's otherwise it's not teleportation. So that means that you can apply something to B as long as it's a quantum gate, so as long as you don't measure, and you will apply it depending on the result AC, the joint result that you obtain. And that will be to transform B to become C. And now you've teleported C. Knowing that again, you have no idea what C looks like, so it could be any general superposition state, and it will remain like so. And that's what's going to be teleported to B. So in practice, what are ABC? And we'll come back to that later. I'll give you an example. These are photons. So we've got photon C and a pair of entangled photons A and B. And what you do is you have a particular quantum state for C. You make a joint Bell measurement, and you teleported that quantum state of C onto B. And now B is now C. And the original C is destroyed because you measured something through the joint measurement with A, which is, again, if you remember, is important that they cannot be C. So in other words, C cannot be in both places at the same time. Okay, it can be in both states at the same time, but it cannot be in both places at the same time. So because there's no cloning possible. On top of the fact that this is also against general relativity, where you cannot have you cannot have two things, identical things, in two different places. That's enough. Right. So we're not going to go through that today because we won't have time. But like we did before, we're going to look into the various steps. So first of all, we start. I'll just give you the lines and the main lines. So first of all, I start with so we start from our general teleporting qubit C. So that's going to be A0 plus B1. Now I put an index here so that, as we will see next time, into the calculation, so that we can see which one's which. So that's on one hand. On the other hand, I've got my entangled state, A and B. So for practical, if I find the mouse again, for practical reason, I will use minus this one, so it's 0, 1, minus 1, 0 for A and B. Then the third step is, so like here, I have 1 and 2, but I can put them into a 3 space by tensor product them. So I can tensor product C and AB. So that's what it's going to look like. Something like A square root of 2, so 0, 0, 1, minus 0, 1, 0, and then B, and then 1, 0, 1, and so on. And so we will do that, but you can start off before if you like. So that is just, we have C and we have A and B. We haven't done anything. Then the next step, which is perhaps the main step is we rewrite. We'll see how we can rewrite this tensor product state in like so. And of rewriting it is what we make appearing. So now a combination of all the Bell states for C and A. I told you that a Bell measurement in a way is entangling C and A. And then we went from 1 to 2. We took apart the B qubit. Because we can do that. We can rewrite in a tensor product, we can rewrite and exchange those qubits. And that's what we do. The reason why we do this, so we make appearing 4 Bell states, but more to the point is we have now 0, 1, or so minus 0, minus 1, or minus 0, plus 1, or 1 plus 0, but exchange, and so on. So we have those particular states. And in particular, this one, which is, in a way, if I remove the minus, or if I put the minus here, it's A0 plus B1. Even though it's on B, but it doesn't matter because qubits are qubits. So it is the state I want to have. But now it's not C index, it's a B index. Okay? And so that's why the next step is to do that joint Bell measurement between A and C, where I'm going to measure one of those. And if I measure this one, I collapse the whole 4 state, and we've seen I make measure, so I collapse the whole thing into one state now, which is going to be the top one. Well, ideally the top one. And if I'm in the top one, so which is in that case, then I have nothing to do because already this is it. I can then disentangle the 2 because B is alone on the right-hand side, and B is now looks like this. So apart from the minus, that is just a global phase, it looks like A0 plus 1B, which is exactly what I wanted to start with. And so what I effectively did is I teleported C from this point to this point. So of course, it can be also a combination of, or it could be a possibility of these 3, but then I would have to make a specific operation or B, you can see, because those, they don't really look like this, so I just need to do an X, Y, and Z, or Z operation in order to have back the original state. And just to give you, and then we'll stop here, what it looks like as a quantum circuit, so we'll come back to that. I've got phi C, I've got A and B. And so first I want to create an entangled state, so I start from the initial state, so I start from 0, 0. I do Adama control naught, remember? So here I will create an entangled state. Then I do a entangling between C and A, Adama gate, and then 2 measurements. I give the result, so you see the double bar is a measurement result. I give the result I found to a gate operation on B, and I apply those gates in order to, or not, in order to recoup the initial state psi, so psi B or QB, that is now become psi C. Okay. So I do a classical adjustment, a classical adjustment from a classical measurement, but it's still a quantum gate to this one in order to recoup the original one. So I teleport it, and this one is dead, this one too. I made measurements, they're done. There's no more quantum, the qubits are no more qubits, it's just information I used. And the other one, on the other hand, carries on his life as a qubit. Right. And so we'll see, we'll come back to that in details, and then what I'll show you is how it was done in practice. Experimentally, so it was done, the first experiment was in 1997, and we'll come back to that. So this is the original setup using entangled photons, and if we have time next time, I'll tell you how we make entangled photons, so how this was effectively done experimentally. So with this, I thank you, and I see you in 3 weeks' time. Thank you.